Hello, it's Scott Manley here. Welcome to my final part of my history of the Thor and Delta Rockets. We return to the start of the 1980s. At this point, the Delta 3000 series had just replaced the 2000 series, bringing with it the larger Castor 4 solid rocket motors to the extended long tank Thor. It was now using the RS-27 engines, which were originally built for the Saturn 1B, and the second stage was powered by the TR-201 engine, which was based on the Lunar Module engines, also used for the Apollo program. There were also a variety of third stage options. Now, Delta was a reliable launch vehicle, but it was about to lose a lot of payloads as NASA were confidently predicting a bold new future for spaceflight, with the Space Shuttle bringing effortless access to space and relegating those old-style disposable launch vehicles to the scrap heap of history, or at least a fiery re-entry and burning up. Yet this didn't happen, of course. It didn't happen right away. There were launches that were planned before the shuttle arrived on the scene, and the shuttle was, of course, delayed. There were satellites that needed polar orbits, so they couldn't be launched from a space shuttle until the Vandenberg launch site was constructed. But there was a definite drop-off in the number of launches. It went down from about 10 to about 6 per year. That was over like a few years. So satellites were being designed so that they could operate on both Delta or the Space Shuttle. The Delta had the Star 48 third stage option, and it became known as PAM, Payload Assist Module, and there was a similar design available for the Space Shuttle. So PAMD was the Delta version, PAM-S was the Shuttle version. You could put a satellite on both either way. The payload interfaces were really similar. Now, PAMD did have some advantages. It had a longer nozzle, a bit more propellant, and more headroom in the fairing compared to the Space Shuttle's version, but satellites would tend to be designed with the Space Shuttle in mind. The PAM was distinct from Delta's numbering and naming scheme, by the way. When this third stage was used, the actual digit for that was 0, and they would add PAM on the end. So, for example, SATCOM 4R was launched on a Delta 3910 PAMD. So in this launch plan from 1981 through 1985, they have 43 potential launches listed for the Delta, with 1/3 of those being backup missions in case there are problems with the Space Shuttle plans. But look, even in the face of retirement, Delta had upgrades for its users. Some were driven by the need to replace the limited stocks of Apollo hardware. The supply of spare TR-201 engines for the second stage was being depleted, and replacements were needed. Other upgrades were needed because the satellites were getting bigger. Like Landsat 4 was an example that was cited that was going to exceed the mass limits of the existing launch vehicle. So an uprated second stage was developed, and what they did was they took the larger tanks from Japan's N2 second stage, and they took an improved AJ10-118K engine, and this was basically a drop-in replacement for the Titan Transstage engine that they'd previously used. They'd managed to get about 6% improvement in specific impulse, mainly by optimizing the propellant injectors. So this design of a second stage would first fly in 1982 from Vandenberg, carrying Landsat 4, and that would use the digit 2 in the third position in the booster designation number. Ultimately, this stage would actually be known as Delta K. Delta engineers even proposed that they could upgrade Delta again to the 4000 series, stretching those tanks and maybe getting more performance out of the PAMD to keep it competitive. But at the time, there wasn't much interest in investing money in upgrading Delta, with Shuttle taking its business. In 1985, there were 0 flights by Delta, and only half a dozen boosters were left in stock, and not all of those were even assigned to flights at the time. But as you know, 1986 changed things, and not in a way that anybody would have wanted. The Challenger disaster not only showed the flaws in the shuttle program, but it also resulted in some hard thinking about the costs that were involved and the benefits of rockets which were flying without unnecessary ballast. But Delta's return wasn't assured by any means. The next Delta launch in May of 1986 failed at 71 seconds after the engine was shut down by a computer. Delta's chance to return to its former glory would come in August, when the Air Force formally asked for proposals for a medium launch vehicle to launch the 20 satellites of their forthcoming GPS constellation. This would be a big contract covering multiple launches, and there were bids from McDonnell Douglas, Martin Marietta, General Dynamics, and Hughes. They all had their own ideas, but ultimately, McDonnell Douglas would win it. So the existing 3000 series Delta came short of the requirements. So McDonnell Douglas looked at ways to enhance the performance without completely redesigning the rocket. One thing they did was they looked at bringing the hydrogen upper stage from the Japanese H-1 rocket back to the US. But they rejected that idea as adding levels of complexity and ambition that was really not compatible with this small extension. Instead, they dusted off those old plans to stretch the first stage one more time. This would actually be the last time they stretched the Delta's first stage, and they called this the Extra Extended Long Tank Thor. So the Castor 4 motors were also replaced with the Castor 4A. Those offered about an 11% gain in performance, mostly by replacing the old fuel formulation with a modern high-energy HTPB version. The only second stage that was used from this point was the Delta K, and the Delta K would continue to fly until 2018 with zero failures over its career. And by zero, I mean there were failures, but it was never the second stage that caused it. So together, these changes would become the 6000 series Delta, or the Delta II. Now wait a second, I hear you wondering out there, what happened to the Delta 4000 and the 5000? Well, those series were interim versions using old booster spare parts that were paired with the Castor 4A boosters that were the right size for a small number of missions. So the 4000 series, they had the old MB3 engines. That's even before the RS-27. They made them essentially a 1000 series Delta with much better first stage boosters. The Delta K second stage and the PAMD third stage, and maybe some other upgrades along the way. This configuration only launched twice, and it took geostationary satellites. One was BSB's Marco Polo satellite that was serving satellite TV to Europe. That was a competitor to Sky. This would ultimately be acquired by Sky, and in June 1990 it would launch INSAT 1D for India, and that would be the last Delta 1 launch. The 5000 series, that had a much more modern RS-27 engine, so it was basically a Delta 3000 with the new boosters. This only flew once. It placed the COBE mission into orbit, the Cosmic Microwave Background Explorer. And so COBE would of course be central to the 2006 Nobel Prize for Physics. So anyway, yeah, the 6000 series Delta II. That would debut in 1989 carrying the Navstar GPS satellites. It would also launch BSB's second Marco Polo satellite in 1990, which would later be sold to a Norwegian operator, resulting in it being renamed to Thor 1. So while Thor launched the Delta second stage, Delta would later launch Thor, completing the cycle of life or something like that. The 6000 series Delta, it would launch 17 times using the last of the RS-27 engines from the Apollo program, forcing another upgrade to the Delta to make up for the lost engines. That would become the 7000 series, and they basically created a new RS-27A design. In addition to these being freshly built engines, the nozzle was changed to give it higher efficiency at altitude, although it did lose a little bit of performance at sea level. But that was acceptable because at sea level, really it's the boosters that are doing most of the work. So for the 7000 series, the Castor boosters were also replaced by GEM 40 boosters. Those are graphite epoxy motors with a diameter of 40 inches. So this used modern, carbon fiber composite casings that were lighter for the same strength. And they also allowed them to stretch the case for, give them more mass or give them more propellant mass. And that gave them about a 17% boost for impulse. That really helped them with their geostationary launch capabilities, which were now up around 1.8 tons. The 7000 series would be arguably the most successful variant of Delta, with over 100 launches until the vehicle's retirement in 2018. It would be the most prolific and reliable US launch vehicle until SpaceX came along and set new benchmarks. Sure, there were lots of GPS launches, but Delta II would carry some of NASA's best-known spacecraft from the 1990s: Mars Global Surveyor, Mars Pathfinder, the first functioning rover on Mars. They took the Near-Earth Asteroid Rendezvous spacecraft, Deep Space One, and the Mars Climate Orbiter. Unfortunately, that one was better known for the wrong reasons. Now, before that, in 1994, NASA was also looking for a medium to light launch vehicle to fill in a gap in their launch capabilities, a gap that many of their new faster, better, cheaper satellites were falling into. McDonnell Douglas reintroduced the Delta II configurations with 3 and 4 strap-on boosters and won this contract. But it also looked at a completely different version of Delta called Delta II Lite. This would keep the upper stages, but it would replace the booster core with a stack of 2 Castor 120 boosters and strap-on Gem 40 boosters. This never happened since there wouldn't have been enough launches to keep it competitive or make it worth developing. Other improvements added over time would include new avionics, new fairing designs, and the air-lit strap-on motors, they would get expanded nozzles so that they would have better performance in the regime where they were actually flying. But commercial payloads were getting bigger and heavier, and to stay competitive and an option for this market, McDonnell Douglas realized that they needed to make big changes to Delta. At first, they once again looked at the hydrogen upper stage for Japan's H-1 rocket, and while that would provide a nice increase in capability without a great deal of new engineering, that alone wasn't going to be enough. The fairing needed to be expanded because the satellites were also getting fatter at the same time. And the second stage was going to be extra long to make Delta II with the hydrogen stage look extra tall and skinny. I mean, Delta was skinny. It was still using the same booster diameter as Thor, which was defined by the need to load it onto aircraft for transport across the Atlantic. So putting that hydrogen stage on top would have made it, look really weird, and that would have forced a lot of changes to ground service equipment. So the Delta III design made some radical changes. The bottom of the Delta with the fuel tank remained the same, but then the oxygen tank became fatter, expanding it from 2.4 meters to 4 meters in diameter, allowing it to be much shorter and making room for a much bigger second stage with all that bulky hydrogen propellant. McDonnell Douglas decided against the Japanese designed hydrogen stage and rolled their own design with a US-built RL-10 engine. So this new Delta cryogenic second stage would be comparable to the Centaur that was being used on the Atlas. The whole stack would still be about the same height as the Delta II, which would limit the amount of changes that they would need to make to the ground equipment to basically adding the extra propellant lines for the hydrogen upper stage. So the first stage boosters were again upgraded to Gem 46 with an extra 6 inches of diameter and an extra 60 inches of length. One important feature of these is to account for the fatter rocket core. 3 of the boosters, which were lit at launch, would have vectorable nozzles to help steer the rocket during the early part of the flight through the thick atmosphere. So while the whole construction looked a lot different, there was still a lot of commonality with the Delta II. Enough commonality that they could use the same pads with some additions, and they could apparently get away, or they thought they could get away, with using the same guidance software on both vehicles. Yeah, that last part didn't quite pan out. In 1998, the first launch of the Delta III, which carried a live payload named Galaxy 10, it ended in disaster, as the more powerful roll control system drove the rocket into a series of roll oscillation that depleted the limited hydraulic fluid used to drive the booster nozzle vectoring. When they ran out of fuel, the nozzles stuck where they were, and the central core with its small engine couldn't counteract those forces. The booster spun out of control. The solution was to update the software to account for these differences to the vehicle behaviour. The second Delta III launch worked perfectly, demonstrating the booster's capabilities, except for the fact that the RL-10 engine in the upper stage, an engine which had an amazing history of reliability, chose this supremely inconvenient moment to have a random failure. The third Delta III launch did demonstrate the entire vehicle's performance, but by this point, changes in management had destroyed any support the program had internally. In the late 1990s, McDonnell Douglas had merged with Boeing, although some say that there was really the reverse. At the time that Delta III was having its teething problems, Boeing was also heavily invested in the Sea Launch project, which was specifically targeting the commercial geostationary satellite market that Delta III was being built for. At the time, international competition from former Soviet states was really making it hard for US companies to be competitive in the launch market, and Boeing's involvement in a Russian-Ukrainian sea launch venture seemed like a more sound financial investment for the commercial market. Boeing didn't want Delta III to get in the way of this, because in hindsight, that was clearly the only problem with the sea launch deal. But the US military were still prepared to pay big bucks for even bigger payloads as part of their evolved expendable launch vehicle program. And Boeing did want a slice of that pie. So while Delta III went nowhere, Boeing began developing Delta IV. But it's not really a Delta. It's a completely new design with the Delta name branded onto the site. It was much larger than any previous Delta, using hydrogen as a propellant. Indeed, Delta IV is apparently the only rocket that has ever been able to launch all the way to orbit using only hydrogen and oxygen as a fuel. The main engine is a Pratt & Whitney RS-68, and I think at the time Pratt & Whitney were part of Boeing, so it made sense for the companies to work with in-house capabilities. The only thing common to the previous Delta rockets was the hydrogen Delta cryogenic second stage from the Delta III, and its associated 4-meter fairing. But that wasn't the only upper stage option for the Delta IV. There was a larger 5-meter second stage for heavier payloads. The core booster could be augmented by solid rocket motors if needed for larger payloads, and for the biggest and heaviest payloads, there was Delta IV Heavy, where they strapped 3 of the Delta IV cores together in a common core configuration. And this monster would be able to launch over 13 tons to geostationary orbit, and while many of its payloads were classified, it was used for the first orbital test of the Orion spacecraft and its heat shield, where they sent it into a higher orbit so it would come back faster, and it was also the best option for launching the Parker Solar Probe, where NASA spared no expense and launched it away from the Earth faster than any other spacecraft in history. And so, Delta III would only fly 3 times, while Delta IV was a vehicle only used for US government projects. But Delta II would continue to fly for a long time, and it would gain one last trick to its arsenal. The Delta II Heavy would be the last version of the Delta developed. It took the larger GEM 46 solid boosters from the Delta III, and that boosted its payload to geostationary transfer orbit to over 2 tons. The best illustration of this capability was the launch of the Mars exploration rovers Spirit and Opportunity in 2003. They both had to launch from the same launch site on the Delta II, but that meant a time delay between the launches as they had to use the same pad. So one had to be launched outside of the optimal launch window and needed more Delta V. So Spirit launched on June 10th on a standard Delta II, and then on July 8th, Opportunity launched on the larger Delta II Heavy. Delta II continued to fly right up until 2018, primarily with NASA payloads. It would launch Messenger to Mercury and the Dawn mission, which would be the first spacecraft to orbit 2 different solar system bodies, the Spitzer Space Telescope and the Kepler Exoplanet Finder, and the final launch, which I got to go to, was ICESat-2. Yeah, I was lucky enough to be there and unlucky enough to have my car break down while parked at the launch site. Don't worry, we did get it towed off base before the rocket actually launched. Yet the final launch of the Delta II was also the 100th consecutive successful launch of the Delta II, with the last failure coming in 1997 with a catastrophic SRB anomaly 13 seconds after launch. Even with this failure, Delta II is one of the most reliable rockets. Delta IV is now nearing the end of its life. It's just too expensive to compete. It was kept alive by the US wanting to have two independent launch vehicles in the form of Atlas and Delta, but now that SpaceX has come along and proven the Falcon 9, there's really no need to subsidize two other rockets. There's a Delta IV Heavy launch from Vandenberg in the next couple of months. It's probably going to be like a KH-11 spy satellite or something. That will be the final West Coast launch of any Delta or Thor variant. And then there's two more Delta IV Heavies from Cape Canaveral, believed to be 2023 and 2024. They're probably geostationary satellites, maybe Orion electronic intelligence satellites. And that'll be the end of Delta. After a career of almost 70 years and over 700 launches, ULA is basically replacing both Atlas and Delta with their own Vulcan rocket. The Atlas and Delta both have their origins in ballistic missiles. Vulcan will be a pure space launch vehicle. But a little bit of Delta will live on a little longer. Remember how Boeing argued that a second stage in common was enough to include Delta IV in the Delta family? Well, it turns out that SLS is currently using the interim cryogenic propulsion stage for its first few launches, and that's basically a Delta cryogenic second stage. So by Boeing's own argument, SLS is just another version of Delta. I'm Scott Manley. Fly safe.